Welcome to Pod4 Journal Club. Today, we're diving into a really cool new paper that's trying to solve a huge problem in AI. And that is, how do you teach an AI to genuinely understand the laws of physics? This research offers a smarter way to guide these algorithms, letting them simulate our world with the kind of accuracy we've only dreamed of. So let's get into it. All right, so first things first, let's get our key terms straight. Physics-informed neural networks, or PINs for short. Now, think of a pin less like a simple pattern matcher and more like a really dedicated physics student. It doesn't just get graded on whether it matches the data. It also gets graded on how well it follows the fundamental equations that, run the universe. It's this two-pronged approach that lets it model some incredibly complex stuff. Okay, so here's our game plan for today. We're going to start with the main problem, why this is so hard in the first place. Then we'll dig into a great analogy the researchers used to help us visualize it. After that, we'll look at the actual results, talk about the trade-offs, because there are always trade-offs, and then wrap up with what this all means for the future of science. So let's jump right into that first big question. Why is it so incredibly difficult to get these pins to learn the right way? What's the big hurdle here? Well, the authors of the paper are really clear about this. Training a pin, they say, is significantly more delicate than standard supervised learning. So this isn't your usual AI training where you just dump a bunch of data in and hope it works. No, this process needs a level of care and precision that most AI training just doesn't. And here's a taste of how it can all go wrong. The signals the AI uses to learn, these things called gradients that basically point it towards a better answer, well, they can just vanish or completely explode. The AI might get obsessed with one part of the physics problem and totally ignore another crucial part. Or it learns the easy stuff first and then just gets stuck, totally unable to grasp the more complex details. And for the really hard problems, like trying to model a shock wave, the whole thing can just fall apart. So to really wrap our heads around this challenge and the solution in this paper, the researchers use a fantastic analogy. Let's walk through it. I want you to imagine you're an explorer. You've been dropped into this huge, mountainous landscape, but it is completely covered in a dense, thick fog. Your one and only job is to find the absolute lowest point, the deepest valley in the entire region. The catch? The only thing you can sense is the slope of the ground right under your feet. That's exactly what it's like for an AI during its training process. And that foggy, mountainous terrain, that's what scientists call the loss landscape. It's basically a giant mathematical map of every possible answer. The peaks are really bad answers with a ton of error, and the deep, deep valleys are the accurate solutions we're looking for. So the whole goal of training is to find a way down into the deepest valley you can. And this is where it gets really interesting, because there are different ways to explore this landscape. The standard methods, what we call first-order methods, are like our poor explorer in the fog, only able to feel the immediate slope. But the new, advanced methods from this paper, they're curvature-aware. It's like someone suddenly hands our explorer a detailed topographical map that shows the shape of all the hills and valleys for miles around. It's a total game changer. I mean, you can imagine, right? If all you know is the slope right beneath you, it's easy to get lost. You could spend forever wandering across a flat plateau, thinking you're getting somewhere when you're not. Or you could get trapped in a super steep ravine, just sliding back and forth, completely unable to make any progress downwards. And this is exactly what happens with most standard AI training methods. All right, so let's get to the evidence. That's the theory, but how much of a difference does having that topographical map really make in practice? Well, the researchers put these new curvature-aware optimizers to the test on some seriously tough physics problems. And this chart really tells the story. What we're looking at is the error rate over time, so lower is way, way better. That blue line is a standard run-of-the-mill optimizer. See how it just flatlines? It gets stuck pretty fast. But now, look at the red and orange lines. Those are the new methods. They don't just get a little lower, they absolutely plummet, finding a solution that's millions, sometimes billions of times more accurate. It's just a whole different level of performance. But it's not just about getting a lower score on a chart. It's about finding the answer that's actually, physically correct. So here, they tasked two different optimizers with learning a simple wave pattern. On the left, you've got one of the curvature-aware methods, and boom, it nails it. It perfectly reconstructs the wave. But on the right, another method just gets completely lost. It's just noise. It found a valley, sure, but it was absolutely the wrong one. Okay, but like any good journal club, we have to talk about the full picture.
The authors are really honest that even these super powerful new methods aren't some kind of silver bullet. There are still some really important challenges and trade-offs we need to think about.
This chart here, it's called a roofline model. It helps diagnose what's slowing a program down. And what it shows is that for some problems, these advanced optimizers aren't limited by how fast the computer can crunch numbers. Nope, they're limited by how fast it can access its memory. The analogy is, having a super detailed map is great, but if it takes you a minute to pull it out of your backpack and read it every single time you take a step, you're not going to move very fast. That's the bottleneck here. So here's the bottom line on the limitations. A better optimizer is a massive step forward, but it's not a magic bullet. For the really tough nuts to crack, like modeling a shockwave, you can't just have a better explorer. You also have to frame the problem in a smarter, shock-aware way. And that memory issue we just talked about, it means that using these powerful methods on even bigger problems is still a major challenge. Okay, so for our last section, let's zoom all the way out. Let's talk about why this is such a big deal. What do better AI training methods really mean for the future of science and engineering? Well, by making this whole training process so much more reliable and powerful, this research basically unlocks the potential for pins. It lets us point them at a whole new class of scientific challenges, problems that until now have been pretty much out of reach. It makes the promise of AI-driven science much more of a reality. And the potential applications here are just so exciting. We're talking about things like accurately modeling the air flowing over a hypersonic jet, or simulating incredibly fast and complex chemical reactions, or even predicting exactly how a new medication will move through the human body. This could speed up discovery in just about every field you can imagine. You know, this work is a huge step towards an AI that doesn't just see patterns in data, but one that actually understands the rules of the game, the fundamental rules of our universe. And that leaves us with a pretty wild final thought to chew on. If an AI can truly master the language of physics, what's to stop it from predicting the future of our climate, our biology, or, well, anything? The possibilities are as vast as those landscapes these AIs are finally learning to navigate.